Okay, so what I want to talk about today was this is actually section 4.7 in Hibbeler, stress concentrations. Or stress concentration factors. So this is pretty a useful idea, although it's relatively simple. The notion is here, we've talked already fairly extensively about this idealized axial loading case, lots of variants of it, maybe a stepped shaft or whatever, where the loading is assumed to apply in such a manner that the stress distribution over the faces is constant, right? So if you cut this, we're assuming that the actual traction over that face resulting from the normal stress is basically uniformed. And so then we can get that stress is the force over the cross-sectional area, right? Well, one thing that's immediately obvious is how do you apply something at a point that then becomes immediately distributed over the area? And we talked about Sullivan's principle. So you have this notion of only really getting this idealized case away from the endpoints or the points where the loading conditions or the constraint conditions are applied, the boundary conditions. Okay? And you get this idealized state. Now, actually, very often, what you see in a lot of engineering structures, and I was trying to see if my office if I had any good examples, but I really don't. But I think this is pretty obvious as well. You might have a plate or something. Okay, that looks very similar, if I drew it well, to something you would expect to see a idealized axial loading, a one-dimensional type of loading on. But, very often what happens is there might be some holes or something where loads are applied or it's constrained, or there might be some other type of hole to allow maybe to lighten the structure or whatnot. Or features where it might neck down and there might be a fillet, something like that. So this is close to, the idealized step. The other one, things you might see are like edge notches like this, right? Sometimes you see those around welding structures, weep holes, so on and so forth. So these are close, and the loading in all these situations is assumed to be axial. So these are close to this idealized situation, but we have these features that change the stress state locally. So what you'll typically see, for example, if we just consider the most simple case that we usually look at is a one-dimensional structure, an axial structure, but maybe with a hole in it. And then if you look at that, what you find typically is if you're far away from the hole, but still away from the end condition, so you get this idealized loading situation, right? If you cut here, you see a fairly uniformed stress state where the stress is pretty constant over the cross-sectional area. It is the P on A. Now, if we draw a section through the hole, if we take a cut through here, what you'll see is something a little bit different. What we'll often see is, so here's the feature. And this depends on the geometrical sort of relations between the hole and the width of the plate and some other factors. If this would be what's called the P on A stress, right? What you actually see is near the hole a raise in the stress. And that raise can actually be significant, sometimes factors of 3 or even greater depending upon the geometries. So this stress exceeds, we'll call this like the max or the peak. I'll put a little star on here. This is greater than the P on A stress. Now these factors happen all the time, and obviously when we're talking about a design situation and we want to know when the structure fails, we actually do want to know the peak stress, because that's often where the failure will occur. And if you design towards to a lower stress, even if you do have a factor of safety, that can cause issues. So, I mean, obviously, factors of safety help take into account some of those things. But when features are large enough, we can actually have a more accurate approach. And this is the so-called stress concentration factor. That's SCF, stress concentration factor. It's usually denoted by K. And what this does is it's a way to get this peak stress. The peak stress is the stress concentration factor times, what would be the mean stress, okay? Very often that stress is going to be the P on A type of stress, okay? So this is a geometric factor. You don't really calculate it. You look it up in tables. This is the stress concentration factor, and it just multiplies this far field load to give you what the actual peak stress is around the feature. Okay. So if your textbook has a couple of nice pictures that sort of illustrate this fact or what goes on. Let's see if I can show you this. Let's zoom in a little bit. There you go. So here you can see what's going on, right? This is the undeformed case, but then you can see what sort of distortion goes on along here, right? And so you can see that it does deviate from this idealized axial stretch. All right. This is another case. This is the stepped shaft with a fillet, okay? And here's this idealized stress distribution, which will be the constant force over that reduced area, but the actual stress distribution looks like that. Just likewise on this one. Let's see, this one's a little hard to get in the picture frame. But again, like this one, here's what you would think would be the average stress, the force over that reduced area. But actually what happens is you get a stress distribution like this. And you can see that the peak amplifies, right? Now how much it amplifies is this stress concentration factor, right? K is the max stress over the average stress. So that's, you can compute the average stress by force over area, and then you can get the maximum stress by multiplying by K. Okay. So the way you normally see this is an example for those two cases. So if you have a stress concentration factor or a design that looks like this, and you want to know the stress raise that happens at these corners because of that stress concentration factor, you find the appropriate table, and then you can actually look up K, the stress concentration factor. So in this case, well, let's do the hole first. So the hole's a little simpler to look at. Let's look at the hole first. So here's the table for the hole, the centered hole in a very long bar. Okay, and this is only a function, K is only a function of the ratio of the radius of that hole over the height of the plate. So if the radius of the hole is half the height of the plate, okay, 0.5, you're over here, and that means the stress concentration factor is about 2.1, all right? If it's at about a quarter, you're about 2.45, all right? So you can look up K. Now, the other one I should probably emphasize is that the average stress you use is going to be the stress over the smallest area. So if you look at this problem, what I mean by that is if you look at this problem, you have basically two cross-sectional areas you can consider. This cross-sectional area or the cross-sectional area that's reduced by the hole. It's the cross-sectional area that's reduced by the hole you use. So that's what they're doing here. You see it's P over W minus the diameter times the thickness. That's that reduced area. So you're just to draw it for that situation. You know what we're talking about. Oops. Oh, you can't see that. There it is. That's supposed to be a circle. It's this area that you use. That's the area, which this is the width, this is the thickness, and this is the diameter, 2r. And there they're saying the area is the width minus 2r times the thickness. And if you apply a force P on there, the average stress is just going to be that P over W minus 2RT. And then you look up in the table. The value K, and that's really a function of, in this case, R over W. And now you can get the peak, the max, is that K from the table times the average stress. That's really it. So these are really straightforward. They're not that hard to do. So we can just do a real simple one. Well, okay. So you can look at the stepped case. Oops, the stepped case. Now the stepped case, you have a family of curves. There's two parameters you're looking at. Basically, the dimensionless parameter of, what do they got it as? The radius of the fillet over H. No, what's H? Should be the height of this. Yeah. H is the thickness of the reduced section. And then you've got this family curve of W over H, so which is the actual step down ratio, right? So depending on what W of H is over H is, you pick one of these curves, and then you figure out off of that what R of H is, and then you pick off your K, and that's the K you use. So let's zoom out. Look at an example. Okay. So I'm just making up some numbers, just to put some numbers in here. All right. Let's say this has a thickness of 1/4 of an inch. We'll give it a length. Doesn't matter actually, but we'll just put, say 10 inches to give everything. And then a height of 2 inches. And this hole, let's say, has a diameter of 1/2 of an inch. Okay? And the load P is 500 pounds. Let's find the maximum stress, the axial stress. And that's going to happen here and here, right at those 2 points. Okay? All right. So we can get the average stress, right? The average stress is going to be the force over the reduced area, right? And in this case, the area, the reduced area, is that area minus the hole. So that's going to be 1/4 of an inch times 2 inches minus the diameter, which is 1/2 of an inch. All right. So that's 1 3/4, and 1/4 of 1 3/4 is. I should be able to do that in my head, but it's a little early in the morning, so. One and 5 3/8, right? 1.3125 inches squared, right? Inches squared. So that means that the average stress is going to be the 500 pounds over the 1.3125 inches squared, which gives me 381 psi. Okay? Now, actually, the stress you see in this far field, you would have a different stress here. The stress sort of in that section would be the 500 pounds over the full area, which is the 1/2 inch squared, because that's this area, 1/2 of it, 1/4 inch times 2 inches, right? And so that would give us actually 250 psi. So you can see this average stress in this section goes up just because the area is reduced. But there still is an amplification of that right at the top and bottom edges of the hole due to the stress concentration factor. So we need to get the stress concentration factor. Now, when we go and look at the table for that situation, well, let's zoom in a little bit. I should make a bigger table. The stress concentration factor is got to do with the ratio of the radius over the width. So in our situation, the radius is 1/8 of an inch. The width is 2 inches. So it's 1/16. Oops, come on. So we're looking at 0.0625. So this is about 0.246, so about up there. And so that gives me a stress concentration factor of 2.75, about, okay? So K is 2.75, and that's from table, what is it? Well, figure 425 in the book. So figure 425 in Hibbeler. Okay. So that means this is going to be 2.75 times the 381 psi, which gives us 1,047 psi. So the stress goes up appreciably as a result of that, okay? So that actually is the peak stress, all right? And that's really all you do with these problems. It's a matter of looking at it. The two things, identify the correct stress concentration table. Actually, in the book, there's only 2 of them. And then figure out the average stress, which is, don't forget, this is the one that's easy to forget. You use the reduced area, not the full area, and then multiply that average stress by the stress concentration factor you see in the table, and that gives you the peak. Okay? And that's it. So let me just mention one other thing while I'm here. So there's a lot of these out there. This is a good reference. I use this a lot. I think a lot of engineers have this in their bookshelves. This has a lot of useful equations for things that we cover in this class, actually. And if you look at this, there's a whole section on stress concentrations. Just a tad bit more. So, for example, here are stress concentration factors K for the case when you have the little edge holes on a plate. Now, this doesn't have a table that you look up, but they have these approximated equations that you can use, and it goes the same way. Okay, so here's an equation for K that you look up in terms of the parameter to use here is H, the depth of the notch, the radius of the notch, over the total width. Okay. Now here's another one for bending. Now we haven't covered bending, but it's a little different if you're in bending. Here's one where you can bend out of plane. Here's one for V-notch. Okay. A notch just on the bottom, notch just on the bottom in bending, V-notch in bending. this sort of T-section, plate biaxial loading. So you can look all these up, you know, elliptical hole, biaxial, right? Sort of a squared out pocket that sometimes you see in weldment structures. A circular shaft. This is a torsion one, I believe, right? Yeah, this is actually torsion, but it's the stress concentration factor you get here for torsion. So it goes the same way, although I don't know if we'll cover explicitly stress concentration factors for torsion, but you do it in the same way. You could figure out on this smaller area the torsional stress, the TC on J, and then right at the fillet, let's zoom in just a little bit, right here at this fillet, you'll get a little amplification of the stress, K. So basically, on this one, I don't want to write my book, but so for this case, the average stress is going to be the TC on J, where J and C are the ones that are computed at this reduced area, right? We're going to use the reduced, oops, you can't see that so well, right? It's the one you see at this reduced area, not the bigger one. Same concept. Then you look up from the geometric factors K, and then what you can find is the stress at the root, which is the max. It's tough to write neatly when it's so zoomed in, is this K times the tau max, right? So they all go the same way. So even though we're just talking axial in this problem, the same concept of the stress concentration factor works over lots of different types of problems. And there's other ones here, you know. Oops, not that one. There's other ones. Okay, so it's pretty useful. It's not that hard. There's actually several related types of corrections to these idealized stresses that have very similar manners. So that's why we cover it, all right? So it's not difficult, but at least make sure you get comfortable with looking them up in the table, making sure you know to use the reduced area, not the full area, right? And they should be very easy problems, and you should be able to get good credit on them, okay? All right, that's all I got to do. I'll do another problem. I'll do some problems later on as well, all right?